Casual Friday here, Kieran Studio, and this is a face mask. We are kind of talking about this today because it's time for Infectious Diseases Part 2. Okay, we're going to keep going over some common human infections, common viruses, common bacteria, common fungi, common worms, and even protein-based human pathogens. Doesn't that just blow your mind? There's a lot of narrative on the upcoming slides that I'll let you read through. I will talk about the highlights. Adenovirus, coronavirus, rhinovirus, all viruses that can cause the common cold. I know that middle guy in there looks a little bit suspicious, doesn't he? Did you know that viruses occupy families and there are many different variants within a family? Coronaviruses occupy a large family of different viruses all over the globe. Some of them cause pandemics. Others just cause the sniffles. Influenza virus. We know it. We love it. We get shots for it. When you get your yearly flu shot, what you're actually getting is science and researchers' best estimate with regard to what influenza viruses are going to be most active in that given year. The different strains of influenza virus, both strains A and B, have different proteins on their viral shell. Since the proteins are what our bodies recognize and mount an immune response to, if we get vaccinated, say with one variant of influenza A, but then another variant with different proteins on its outer shell gets into our body, we're not going to have vaccine protection, so to speak. One of the interesting things about influenza, and especially influenza A, is that the hemagglutinin and the neuraminidase proteins have a high rate of mutagenicity, meaning that their genetic material is oftentimes taking on new mutations, producing different proteins. This is why you can't get one flu shot that lasts your whole life. If those proteins are changing, science and researchers are chasing after what changes occur to design vaccines that follow with those mutations to those proteins. It's generally accepted that influenza travels person to person via respiratory droplets. And those are, think of them as kind of big droplets of water that can contain many copies of the virus in them. The debate over aerosols, which are tiny droplets that may have just a fraction of virus in them, the debate over aerosols is still going on. And you hear the same debate with coronavirus. On a respiratory droplet, if you have, say, 1,000 copies of the virus, that's probably enough to set up shop, whether it's influenza or coronavirus, in another person. But if you got a tiny aerosol passed just from speaking or just from breathing, and it only has 15 copies of the virus on it, is that enough to infect another person? This then goes back to the concept of dose. How much virus does a person need to actually get infected? Epstein-Barr virus is in the family of human herpes viruses. And human herpes viruses are fascinating. Here's the reason why. Human herpes viruses have figured out a way to essentially escape immune detection. And they do so by infecting cells of the body that our immune system essentially can't uncover or discover. Epstein-Barr virus is a great example. EBV is the human herpes virus that causes infectious mononucleosis. Almost everyone will get EBV at some point in their lifetime. Whether or not you're symptomatic with mono will be different person to person, but infection with EBV is pretty much a guarantee. So the interesting thing about Epstein-Barr virus and its hiding capability is that it goes on after the initial monoinfection to infect B lymphocytes. So check this out. So the way it escapes immune detection is by infecting cells of the immune system. Isn't that cool? HIV does the same thing. EBV infects B lymphocytes. HIV infects T lymphocytes, specifically CD4 cells. These viruses have learned that to escape immune detection and eradication, they can do this by infecting the cells of the immune system. And this is how viruses such as Epstein-Barr virus and HIV become chronic long-term infections and subsequently cause so much in terms of human disease. So while we're on the topic of, the big family of human herpes viruses, why not just mention HSV1 and HSV2, which are arguably the most popular in their family. HSV1 and HSV2 commonly infect distinct parts of the body, but I will tell you right now, they're not specifically limited to up here versus down there. With Epstein-Barr virus, it used B lymphocytes to escape immune detection. HSV1 and HSV2 use neurons. They infect neurons and are able to escape immune detection by using a neuron as a hideout. Pretty fascinating, isn't it? A common feature for many herpes viruses, including HSV1 and HSV2, is periods of exacerbation and then dormancy or latency. So you'll get your initial infection with HSV, cause a little outbreak maybe on the lips in terms of cold sores, and then there's some immune response to the skin area. That's taken care of, but the remaining virus then actually remains dormant or latent within the local neurons until some later triggering event. And you'll hear patients say, well, whenever I get stressed, I get a cold sore. When there's some other event in the body, an infection, human herpes virus pops back up. Hey, we're still in the herpes family. Woohoo! Have you heard of herpes zoster or shingles? Varicella zoster is human herpes virus 3. This comes from the virus that causes chickenpox, remains in our bodies for a good portion of our lives, and then typically later on in life, decades later, and oftentimes after some degree of immunoincompetence, people will get a re-exacerbation, a flare-up, if you will, of human herpes virus 3, varicella zoster, better known as shingles. Much like herpes 1 and 2, this virus also chronically infects neurons. So the classic clinical presentation of shingles is herpes-looking vesicular lesions with a dermatomal distribution. Remember your dermatomes, right? So lesions along a dermatome, say around the side, wrapping around from the back to the side, or something similar to that. Remember that for clinical practice. Older adult, herpes-looking lesion with a dermatomal distribution. So at the top of the slide it says, hey, do we all have herpes? And the easy answer is, yeah, probably. So check out this chart. Don't try to memorize it. Just read through it for kind of a general idea of the herpes virus family, where these viruses like to infect, and some cool take-home points. So if you look at the tissue tropism column, that's describing where these viruses have evolved to live within our bodies. Now, I actually don't like using the word live and survive when it applies to viruses because viruses are not living things. But, for lack of a better term, we often do use those terms when we're talking about viruses. So in human herpes virus, they have evolved to reside in our bodies in areas where they evade immune detection, be it in a neuron, be it in a B lymphocyte or a T lymphocyte. These viruses are not dumb. The other thing they can do is they can set up chronic infection, which then can lead to chronic inflammation. Additionally, some human herpes virus, and Epstein-Barr is infamous for this, integrate their viral genetic material into the host cell. This causes issues with relation to transcription and translation, and can alter the host cell in such a way that later on down the road, usually with other mutations, a cancer may develop. This is one of the ways that people develop lymphoma, a cancer of white blood cells. West Nile virus is all over the United States. There's a very good chance if you're outside and you're in an area that it's known to exist, that you can be infected with West Nile virus. Here's the good news, probably not going to do anything. Here's the bad news. In roughly 1 in, say, 150 to 200 infectees, West Nile virus can take on very severe complications. So rather than just being a usual viral illness that runs its course, it can progress to something called West Nile encephalopathy. Yeah, serious business. That's where the virus itself infects the brain. Fairly rare, you're probably not going to see this all that often, but it's something to be considerate of. And when patients come in with encephalopathy or encephalopathic styled symptoms, West Nile encephalopathy will be in the workup, because we do live in an area where that virus is known to exist. Here's another mosquito vector viral illness, Zika virus. This was in the news a whole heck of a lot a couple years back, and it was in the news for a reason kind of similar to West Nile, but the particulars of this were that if pregnant women were infected with Zika, it wasn't them getting encephalopathy, it was their children, their unborn children, who were born with microcephaly and then, or thus, microencephaly. Small head, small brain. In non-pregnant individuals, Zika just seemed to kind of run its course like a normal viral illness. So it was within pregnant women that the focus really was. And I have to say, I was pretty fascinated that it seemed to be limited to south of the border of the United States, as if mosquitoes pay attention to boundaries. Ebola virus kind of pops in and out of the news periodically. I bring it to people's attention in a patho class because I respect the contrast that Ebola has in terms of a viral illness compared with your average rhinovirus or adenovirus that causes the common cold. One of our principles of patho is that, generally speaking, viral illnesses are not as severe, not as symptomatic as bacterial illnesses. Ebola virus goes against that. Ebola virus has all the usual viral symptoms, but they're ramped up. Plus, you have the possibility of hemorrhage. And what's really frightening is that Ebola virus has a mortality of 40%. That's humongous. By way of comparison, the pandemic that we are currently in with coronavirus has a global mortality between 2 to 3%. In any given year, influenza virus has a mortality of around 0.1 to 0.5%. 40% is frightening. Aren't you thankful Ebola's not a respiratory virus? Yeah, me too. Because it's not a respiratory virus, its ability to spread globally and to take on pandemic status has been limited. Okay, so that was just a brief chat over some common human viruses. Let's switch gears. Fungi can infect humans too. Candida albicans is a very common fungus that can cause all kinds of fungal infections within humans. Clinically, you're going to see this very commonly in a condition called thrush, which is an overgrowth of Candida within the mouth, and it causes a whitish coating to the tongue. The clinical term that you'll hear is thrush. The technical medical term is oropharyngeal candidiasis. Overgrowth of the Candida fungus is most often seen when people take antibiotics or, say, chemotherapy, alter the normal flora of the mouth, and it allows candidal overgrowth. You like fishing? Yeah? Oh, drop a line in the lake, relax. What do you bait your hook with? Worms? Tapeworms, perhaps? Ringworms? Helminth infections are worm infections. I mean, why should just, viruses, bacteria, fungi, why should they have all the infectious fun? Come on, the worms want in on the action, too. Nice thing about worms is that, if you don't eat, raw meat and other places that worms are known to inhabit, it's a little bit harder to get a worm infection. So, probably not going to see too many cases of tapeworm in your life, I'm guessing, but it's out there. And it does make you a little bit kind of, ooh, worms. Worms can infect us. Okay, mark this in your notes, because every year I say the same thing, saying it again this year. Prion diseases, such as Creutzfeldt-Jakob and bovine spongiform encephalopathy, are, to me, fascinating. Check it out. So we've talked about viruses infecting humans, fungi, bacteria, worms. Did you know that a single misshaped protein called a prion can also infect and kill? What? Prion diseases are literally just misshaped proteins. Creutzfeldt-Jakob and its bovine parallel, bovine spongiform encephalopathy, are prion diseases. Misshaped proteins that get into the human brain and cause death. There is no cure for prion diseases. The other thing I find fascinating about them is viruses are non-living infectious agents. Prions are basically just a piece of what a virus is. A virus is genetic material with a protein shell. A prion literally is just a protein. That's crazy. How could that be an infectious agent? Blows my mind. How do prions get transmitted? Normally by ingestion. The animal or the human ingests the proteins. Somehow, I'm still floored by this, they survive the acid bath, that is our guts, get absorbed, and then find their way into the central nervous system. It's fascinating. Prion diseases were first identified in the early 80s. We still honestly don't know that much about them. If you want a very interesting read about the transmission of prion diseases in human societies that practice cannibalism. Specifically, human societies that cannibalize the brains of the dead. For the STDs, I don't have too much to say. Chlamydia, gonorrhea, pass through, you know what.
Giddy up, papa, papa, mau, mau. Giddy up, papa, papa, mau, mau.
Chlamydia, gonorrhea, two tremendously common sexually transmitted diseases. Typically, people are symptomatic with these things. Stuff is getting all inflamed down there. It burns. It's got an odor. These are not hard to figure out. And thankfully, they're very responsive to antibiotics as well. I'll point out that because gonorrhea-based conjunctivitis in children can lead to blindness, prophylactically all newborns will get antibiotic prophylaxis against gonorrhea in the form of an ophthalmic ointment. So what happens to that person who gets the gonorrhea, gets a little bit of the chlamydia, mixes it all up, and then never gets treated? That's the most common clinical scenario that eventually leads to a condition called pelvic inflammatory disease. And those of you that are working in women's health, and especially primary care, will probably see cases of PID. And at least to me, they've always been head scratchers, but pelvic inflammatory disease is essentially the chronic inflammatory changes caused by STDs that went untreated. Oh, syphilis. Oh, man. Okay. So here's a treponemal STD, arguably the most morbid of the big three: chlamydia, gonorrhea, and syphilis. And here's the reason why. Syphilis has stages of infection if it goes untreated. A primary stage, a secondary stage, and a tertiary stage, which some people call neurosyphilis. If that sounds bad to you, that's because it is. Syphilis is a very significant sexually transmitted infection that does require treatment because the long-term consequences, the sequelae, are so significant. Speaking of neurosyphilis, tabes dorsalis is a very specific presentation of neurosyphilis whereby patients present with difficulty walking, called ataxia. As you can imagine, there's all kinds of diagnostic tests. PCR means polymerase chain reaction. That's a genetic material test that can find genetic material specific to syphilis. The VDRL test is used to test for the presence of syphilis. I don't think for this class memorizing these tests are necessary. I'm just mentioning them because you'll see them starting in your med-surg classes. And we should always remember that syphilis is also a great stain on the integrity and ethics of research in the United States. If you want to know more about it, look up the Tuskegee Syphilis Study. Genital warts are caused by the human papilloma virus, and as the name implies, they cause papillomas. And we've already learned that the suffix oma always means a mass. HPV virus is everywhere, and most people over the course of their lifetimes will become infected with HPV. Here's the good news. In most people, it's a normal viral infection. It gets in, it infects epithelial cells, say in the cervix or somewhere along the genital tract. It runs its viral course, and that's it. Normal viral illness. In some people, for reasons that aren't entirely clear, much like Epstein-Barr virus, human papillomavirus takes its genetic material and integrates into the host cell's genome, altering that genome, changing genotype, ultimately changing phenotype, and potentially taking on cancerous characteristics. For HPV specifically, this is a fun one to think about because it brings us all the way back around to oncogenesis. HPV is probably the most well-researched virus in terms of viral oncogenesis and how it goes on to cause cervical cancer. In HPV specifically, when the viral DNA integrates into the host cell's DNA, it creates proteins that are no longer used. I'm going to go slow here. The proteins from the viral DNA are no longer used to make new viruses. So those proteins have a binding affinity for two tumor suppressor proteins within the cervical epithelial cell. And those oncoproteins are called P53 and retinoblastoma proteins. Two very important tumor suppressor proteins. You already know, throwing off the balance between oncogenes and tumor suppressor genes and their related proteins can set up a scenario whereby cancer is the end result. Here we have a very well-researched pathway by which a virus can upset that balance. So we've talked a lot about infectivity of various viruses, bacteria, fungi, helminths, proteins, which are prions. Are you feeling a little woozy yet? Are you getting itchy? Infectious disease is a fascinating area because there's so much that can infect us. But please, whenever you're thinking about any infectious agent, please go back to kind of the principle of infectivity. It's not just what's infecting us, it's how much, which is the dose, and what kind of immune response do we generate to that infectious agent. There's always more to consider other than just the infectious agent itself. Talk to you soon.